lecture, we are going to venture into the orthogonality principle under our wide spectrum linear estimation of a random variable. Okay, so what are the assumptions? The assumptions are the same as given in my previous section lecture. Now we have n plus 1 random variables as usual. So we have n plus 1 random variables as usual. It is going to run from x0, x1, x2, etc. up to xn. Okay, whose means and second order moments, whose mean and second order moment are given by the notation which we are going to use is the same as before. E of xi will be denoted as eta I, and my E of xi minus eta I into xj minus eta j, this will be represented by mu ij for all I comma j running from 0 to n. Okay, so let us take this equation as equation number 1. Now x0 is desired to be approximated from x1 to xn as usual. So how do I represent my x0 tilde? It is nothing but a1 x1, a2 x2 plus etc. I will run to an xn plus b. Let me take this as equation number 2. Now the error E is given by, in general, epsilon is also used to notate this. So the error, let me call it as epsilon, is given by x0 minus this approximation x0 tilde. So this value is nothing but x0 minus, I will have a1 x1 plus a2 x2 plus etc. plus etc. an xn plus b. Now with this equation as equation number 3, let me move forward. I need to obtain EMS, mean square error. This is nothing but my E of our epsilon squared. So E of epsilon squared is now going to be my E of, I will have x naught minus, I can take it as summation I equal to 1 to n ai xi minus b, this whole square. So this becomes our equation number 4. Now what is it that we normally do? We will take partial derivatives with respect to ai's and b and then equate it to 0. So same thing we do here by taking partial derivatives with respect to ai and b and equating to 0 and equating to 0. We have been doing this quite a number of times in this series of lectures. So I am directly giving you the answer. We get E of x naught minus this summation, let me expand over here, a1 x1 plus a2 x2 plus etc. plus an xn plus b into xi equal to 0. Now please consider this. Let us take this as our equation number 5. We also have our b is given by eta naught minus, you will have a1 eta 1, a2 eta 2, etc., etc., an eta n, leading to our equation number 6. With this on hand, we now have to resolve. So what is the error? Clearly, our x naught minus a1 x1 plus a2 x2 plus etc. plus our an xn is the error. Okay. Now, one more thing what I would like to tell you is we can interpret this equation over here, this equation number 5. So, 5 could be interpreted as, this equation number 5 could be interpreted as the error is orthogonal. The error is orthogonal to each member of the data. How am I getting this? Please look at this equation. I will have a1 x1 xi, x2 xi, xn xi. All these values tend to vanish. So of the data and 6, this equation, sixth equation. What is our sixth equation? The equation regarding our b, that is our sixth equation. So the sixth equation gives the optimal solution for b. This gives the optimal solution for b. Okay, this statement is the first part. This statement is the first part of the orthogonality principle. Okay, so this is the first part of the orthogonality principle for minimum mean square, for minimum mean square error linear estimation. Okay, now we have to move on to the second part. So what is your second part? Here the second part deals with evaluation of EMMS. So it deals with the evaluation of minimum mean square error, minimum mean square error, that too in the linear case, for this optimal estimator, for this optimal estimator. So how do I go about the second part? This is the question now. Already we have seen several times, we know the formula, so we start with EMMS. This is nothing but we just need to take expectation of, I will have x naught minus of this a1 x1 plus a2 x2 plus etc. plus an xn plus b. This whole term, maybe I can use a different color for the bracket so that it will be very clearly seen for us what we are multiplying where. This whole thing into, this whole thing into x naught minus b. Let us now evaluate this. how am I going to rewrite this? I am going to rewrite this x naught minus b from the first case. So this value would give me an expectation of I will have x naught minus, I will have this x naught minus all these terms a1 x1 plus etc plus an xn plus b, let's close the bracket, into, when I go for this x naught minus b, again I will have, replacing this x naught minus b, what is this, x naught tilde minus of b. Look into our second equation. Please look here. You have x naught. Pull this b to the other side. You will have x naught tilde minus b is nothing but our a1, x1, etc. up to an, xn. Okay. So come here. So this is nothing going but it is just going to be my a1, x1 plus a2, x2 plus etc. plus an xn, and now let me close the bracket. This I am getting by equation number 2. This is how I got this term. Okay. Anyway, this equation, we will term this equation to be equation number 7. Okay. Now look at this. The second expected value, that is this term into this term, will now turn out to become 0 for us. So only the first term is going to exist for us. Therefore, from equation number 5, from equation number 5, we will be able to see our EMMS equal to, since the second term becomes out of range, only the first term is existing for us, this value will now turn out to be expectation of, I will have, open bracket, x naught minus eta naught, I will have x naught minus eta naught minus a1 into x1 minus eta 1 etc minus an into xn minus eta n. This is what I will be left out with. I have done a little bit of algebra over here by multiplying and expanding and finding out the second term becomes 0. Okay. So using this value, this is nothing but, I would just equate this to, all these are numbers and values together. So this would give me x naught minus eta naught minus of, I will have a1 eta 1 plus a2 eta 2 etc up to eta n. Okay. This into minus of, I will be having x naught minus eta naught minus of a1 minus, I will not have minus, I have multiplication, a1 eta 1 because a1 into e of x1 eta 1. So minus of a1 eta 1, and then minus of minus will become plus. So I'll have minus a2 eta 2 and so on. Now try to expand this and check if you are getting the same value as you are getting here. So this would be minus of a1 eta 1, a2 eta 2 plus etc plus an eta n. So this is what we would be getting. And however, for this we need to also take the value and simplify it further. So we can make use of the mu ij expression to proceed further. So the first expected value, therefore, the first expected value gives sum of this gives the sum of covariance of x naught and xi. Covariance of x naught and xi. The second expected value is 0, and the second expected value is 0. Why this becomes 0? Since it gives the weighted sum. Since it gives the weighted sum of the central moments of all our xi's. So E of xi minus eta I, which are 0 by the definition. Okay, hence my EMMS is now reducing to, I will have sigma x naught squared minus summation I equal to 1 to n mu 0 I into our AIs. So this is the final result which we are getting from here. What is our mu ij? Please recall. I suppose in the beginning we have mentioned what our mu ij was. Mu ij is E of xi minus eta I into xj minus our eta j. So now please look at this eta I, this also become eta j. So now come over here, look into this equation where we are moving above. Here you have xi minus eta I into xi minus eta j. The same formation which leads to our EMMS value as sigma x naught squared minus summation I equal to 1 to n mu 0 I ai. Okay, thank you.